So it's really great to be here in the Northeast, especially when it's not raining. It's really nice. So I'm going to tell you about a colleague of mine at Microsoft Research, Butler Lamson, who has a useful way, I think, of classifying how we've used computers over the last 60 or so years. And so the third age of computing, the one we're in now, he talks about computers for embodiment. What do I mean by that? I mean by the applications of computers which engage with the physical world through all sorts of sensors and things, but do things intelligently on our behalf. So those are the sort of applications we're beginning to see, and we'll see a lot more of. So I should explain that I first thought about this when I was shopping with my son Jono in his Volkswagen Touran. So we went shopping, and I went back to my house, and there was a very small parking place. And he said, no problem, and he parked alongside it and pressed a button. And it was really kind of spooky watching the wheel turn, and the car parked perfectly. And that's an embodied application. That's something we would like to happen. A few months earlier, I'd been in Berkeley, California, and I talked to my friend Horst, and he told me this story. He'd been driving from Berkeley to Livermore, about 40 miles, to see his boss, and he took a company car. When he got to Livermore, his boss, to his surprise, said, I'm sorry, Horst, but I have to reprimand you for speeding on the way here. His car had emailed his boss. So that's embodied too, and there can be some surprises. So a little bit about myself. I used to be a physicist, a particle physicist looking at elementary particles like the Higgs boson that they've recently found at CERN. But I went on sabbatical at Caltech in 1981, and I attended a lecture by Carver Mead. He's the Gordon Moore Professor of Computing at Caltech. And this man here is Mr. Gordon Moore. He was one of the founders of Intel, and he made, as you know, as we saw, he made the prediction from these 4 points in 1965 that the number of components on a transistors on a chip would double every 18 months or so. And as you see, it's brilliantly held true. So Carver Mead was the man who explained why it was true, and he made the prediction. I remember very well the words that he said, there's no engineering obstacles to making the chips smaller, faster, and cheaper for the next 20 years. And as you can see, he was wrong. We're still going. But it is going to slow off at some point. And in the near future. So this was the chip that excited me. It was a chip that Intel produced in 1971. It was a microprocessor. A Japanese company had asked Intel if they could produce a range of chips for their range of calculators with different capabilities. But Ted Hoff, the engineer there, said, well, why don't we produce one chip and then we can program it so it does different things? And this was the beginning of the microprocessor. And of course, Intel was sitting on a gold mine. Now you find these things in refrigerators, in cars, in computers, everywhere. And so that was the beginning of for me, my infatuation with computers. Why did I care about them? Well, I was doing calculations in particle physics, and I needed a supercomputer. Now, professors don't have a lot of money, and supercomputers are expensive. But what we could do is buy lots of these. So you could take 100 of these or so and put them together. And it was like, the difficulty, of course, came, you had to program them. So it was like getting 100 rabbits to pull a plow rather than an expensive ox. So there is a downside. But that's all you could do as an academic. All right. So this chip had a few thousand transistors on. And where we are now is the state of the art. Is there's an Intel Xeon chip, which has a few billion transistors on. And that's really, a million-fold increase. And the Intel CEO once said, if car technology had kept up, a VW Beetle would be able to have a top speed of 300,000 miles per hour, travel 2 million miles on a tank of fuel, and cost 4 cents. So we have some way to go. So I think that is really the achievement of computer science. It's dealing with the complexity of making billions of devices actually work together. And so this is the science that's changed the world most in the last 50 years and will continue to change it. And yet I see lots and lots of popular books about physics, about astronomy, about genetics and biology and so on, but I don't see many books about computer science. So this is an attempt at writing a popular book on computer science, and I'd like just to show you where we came from, where we are now, and where we're likely to go in the future. So this is Butler Lamson's third age of computing, and he talks about the classification of the applications in the following way. The first 30 years, from about 1950 or so, we were doing calculations with them, designing airplanes and things like that. And then we connected them up, and we've been doing applications with connectivity, all the wonderful things we've seen with the internet and the web. But now we're getting to where we're going to do these embodied applications which have intelligence in them and can do all sorts of clever things. You saw some nice things with Andy's talk this morning. So what I'd like to do is just say briefly a few things about the first stage of computing, where it all started. So it started in 1945 with this machine called the ENIAC, and here is John Mauchly and Presper Eckert, the two engineers at the Moore School of Engineering in Philadelphia. And the machine was big, and I mean really big. It was 8 feet tall, 80 feet long, and had over 17,000 vacuum tubes. So it was a big machine. It was built by the military because they wanted it to calculate artillery tables for new types of guns, and they had a backlog. It came too late to do that, but it did actually do calculations originally for things like the atom bomb and things like that. And then we got into the stage of the 1950s and 1960s when IBM was the dominant company, and this is the sort of scenario. You had your program on a punch cards, and you handed it to this sort of priest of this machine. He was the only person allowed to touch it, this computer operator, and that was how you interacted with these sort of godlike things, these computers. Fortunately, in the 70s and 80s, things got a little more relaxed. And I'd just like to say a little bit about this machine here. This is the Alto, and it was produced by Xerox with their research center in Palo Alto. And the people who produced it was Butler Lamson, Chuck Thacker, and Alan Kay. And it was the first recognizable, in 1971, the first recognizable personal computer. It fit under a desk, it connected to other Altos via a network through the research center, and it also connected to a laser printer, which they'd also invented. But more to the point, it had the sort of programming interface that we would all recognize. It had overlapping windows, it had a mouse, it had drop-down menus, and of course it had the first WYSIWYG, what you see is what you get, word processor. So that was the Alto, and it was enormously expensive. They used huge amounts of memory, and that was very expensive at the time. But they understood Moore's law. So they called it a time machine. And in 10 years' time, that would be cheap enough for all of us to have one. In the middle is an Apple II, and that was an interesting time because instead of the computer companies leading the way, or the academic computer scientists like in universities, this was the time of the hobbyists. These are people who wanted to build things for doing games and all these sort of things. And so this is the time that Bill Gates and Paul Allen started Microsoft. This is when Steve Jobs, Steve Wozniak started Apple and so on. And they actually were the people who pioneered the microprocessor into everyone's lives. And of course, it was given a stamp of approval in '81 by IBM, who introduced it into industry with the only application, really, that this one didn't have. It was the spreadsheet. And that was the killer app for getting it into industry. Then the second age of computing was the age of when computers communicate. And this was the brainchild of a professor of psychology at MIT called J.C.R. Licklider. And he had the idea of connecting all these expensive computers in these university research departments, putting them together so we could each share the machines. And he took that when he went to a funding agency in the US called Advanced Research Projects Agency, usually now has a D for defense in front of it. And he then had this brainchild of building this network. And His successors then got the money and built it, and this was what the ARPANET looked like in 1969, 4 nodes all on the West Coast, not a very impressive network, but 4 years later it covered the whole of the US, and also there was a node in University College London in the UK, which I remember using to connect to a computer in Caltech. But of course, that wasn't, sharing resources wasn't the killer app for the ARPANET. The killer app was email, which we all use. And of course, this is the situation now. Literally billions of devices connected to the internet, which is a network of networks, and we now have over 3 billion people using the internet. That's over 30% of the world's population. And it's really been incredible. However, it needed someone to simplify using it, and this is the person who did that. This is Tim Berners-Lee, a physicist working as a programmer at CERN. And he had the idea of using a technique invented by Ted Nelson and Doug Engelbart, which was the hypertext link. You could go from a place in a document to a place in another document. You didn't need to read them linearly. And so he had the idea of doing that from this machine to a different machine over the internet, and that was the birth of the World Wide Web. And it led to all sorts of new applications, web browsers, of course, and search engines. Search engines, well, they're these two guys. They were students at Stanford. This is Sergey Brin and Larry Page. And the leading search engine in 1998 was a thing called Alta Vista. I remember using it, but nobody knows it now. But these guys, in their student-like way, thought they had a better way of finding out the most relevant page for your query. And they instead of focusing on the number of times the word appeared in the page, they figured out the importance of the page by the number of links coming into it and the number of links coming into the site that pointed to your site. And so using that algorithm, which they call PageRank, and the algorithm is just really a set of, it's like a recipe, it's a set of steps you tell the computer. They had this wonderful machine working on Stanford campus, this search engine. And then they tried to sell it. They tried to sell the idea to Alta Vista. They tried to sell it to Yahoo, and they both said no. But one of the co-founders of Yahoo, David Filo, himself an ex-graduate student from Stanford, said, well, why don't you start your own company? So they did. And we all know what happened there. So this is actually now when you put those two things together in the cloud, the Google, Amazon, Microsoft, Facebook, Apple, IBM, all of these people have these big data and compute centers in the cloud connected by huge amounts of bandwidth. Why is that important? Well, it changes a machine like this into something very interesting. Now, I imagine most of you have iPhones. Because I worked at Microsoft, I have a Windows phone, and there's no TDC app for the Windows phone, I notice. But so you will speak into your phone to Siri. I speak to Cortana, and I would say something like, Hal, open the pod bay doors, all right? And the signal, actually, no, don't laugh, its signal goes up to the cloud, and all the calculation is done, and it has to interpret the speech, understand it, and give me an answer. So it comes back saying, I'm sorry, Dave, I can't do that. All right? But it changes these things into powerful computers, and that's really the liberation. And now you add big data from all the sensors you saw that Andy had, and all sorts of different sensors, and you add that with new exciting algorithms coming from computer science, things like machine learning networks and things like that, and I'll say a little bit about that. And you have these embodied applications coming up. So let me show you an example of an embodied application, a modern one. So this is actually...
They see what's ahead and respond right in the moment. A radar sensor and advanced cameras, including a new stereoscopic camera in the windshield, allow intelligent drive to recognize objects 360 degrees around the vehicle. Radar sensors give it foresight. Long, short, and multi-range radar scan the environment in front of the car, behind it, and out from the rear corners. The intelligence comes from insight. Advanced computing power interprets what it sees, determines the best response, and springs into action faster than humanly possible. The systems of intelligent drive can recognize a pedestrian entering your path, vehicles ahead slowing to a stop, and even cross traffic at a nearby intersection. The moment it does, it lets you know. As soon as you brake, even if it's too lightly, intelligent drive can increase it to the precise amount needed, even applying full braking power. And if you don't respond, it can initiate braking on its own, all to help reduce the chances or severity of an accident.
So that's the sort of embodied intelligent application with all the sensor information that you want to do. But what you have to do is use that information to identify a person or a car or an object, and that you need to have clever algorithms. So this is an example of one of the algorithms. It's a very early one. It's a neural network. It's an artificial one, of course. In your head, you have billions of neurons. Here, I've got just a few. And the analogy is that neurons have lots of connections. In your head, you have billions of neurons, but trillions of connections. This is a much simplified, but it works the same way. You get lots of inputs to a neuron. When you get above a threshold, it fires. And so what you can do with this network is you can train it. So you have a series of outputs and you have a series of inputs, and you adjust the connections in order to make sure that it recognizes. So for example, number plate recognition, it can recognize the number plate letter and the numbers, and it can actually then, you train it on a set, and when it sees one in a camera, it'll send you a ticket, and so on. So these are the sort of neural networks that is only one example of a machine learning algorithm. Give it more data, it improves. There's great excitement in the field at the moment because it's networks like these. I've only shown 3 interconnecting networks here, interconnecting layers. You can imagine more, and these deep neural networks are really helping the industry and the research community make real progress in some of these really hard problems. Like, it's easy for a 3-year-old child to look at an image and tell the difference between a dog and a cat. It's actually quite difficult for computers to do that. But now we're hoping to do that and make progress on speech recognition as well. So let me show you, however, as always, there's an upside, but there can be a downside. So let me show you this.
This is a regular new car. The masking tape is only there because we agreed to obscure its make and model.
We'll give them the illusion they control the car for now.
Kaufman has been working on this for 5 years with multiple research teams.
You want to hit the fluids?
Oh my gosh.
There we go.
There we go.
What's that? What's that? What's that?
That's the windshield wiper fluid.
No, wait. So this is something that a hacker has...
That's right, a hacker. Like, obviously, you didn't turn on the windshield wipers.
Using a laptop, the hacker dialed the car's emergency communication system and transmitted a series of tones that flooded it with data. As the car's computer tried sorting it out, the hacker inserted an attack that reprogrammed the software, gaining total remote control.
Oh my God.
The horn.
They're doing that?
They're doing the horn.
They could control the gas, the acceleration. They could control the braking.
That's right.
And they could do this from anywhere in the world.
So just stop at the cones here.
She thinks she's going to be able to stop right at those cones. Let's make sure that she can't, and she's going to drive right through them.
All
We'll
right.
have complete control of that brake.
All right, there we go.
Oh, no.
The brakes
I
didn't
cannot.
work,
Oh my
right?
God. I can't operate the brakes at all. Oh my word. That is frightening. That is frightening.
So there are downsides too. And these are really serious things we need to think about with all these applications, because many vulnerabilities are possible. But you will see enormous numbers of applications, these are just 2, with intelligence in them. So this is Apple's iWatch, and it can not only tell you the time and your email and texts and tweets and things like that, but it can also monitor your blood pressure, how many steps you did, whether you've been rugging, your GPS, it knows exactly where you are. It can text your doctor if you're having a heart attack, and all these sort of good things that it can do, but it can also monitor exactly where you are, and somebody can hack that and know exactly everything about you. This is another one for Microsoft Research on the right here. This is where I can speak into Skype now in English to a colleague in China, and my voice comes out speaking Chinese in China. And if you can make that really reliable with these deep neural networks and so on, then it's really going to transform how people work. So, is this intelligence? Well, there's a distinction, as we heard this morning from Luciano, between weak AI, which I've shown you examples of things which look as if they're intelligent, but actually it's just brute force doing it, or strong AI, where there is real intelligence and independence of thought, self-awareness, like all the robots in the stories and things we heard about this morning. So you might think playing chess requires intelligence, and this is Garry Kasparov losing to Deep Blue in 1997. But Deep Blue was really just using brute force. It was really just going further ahead than a human do. It didn't play chess with intuition and patterns as well as analysis of positions. It just did brute force. So that's not real intelligence, that's simulating intelligence. IBM did another impressive example of having a machine which won at this rather obscure quiz game called Jeopardy! There the host gives you the answer to the question, and you have to guess the question, right? So it's slightly obscure. You also need to feed the computer all sorts of knowledge. Here you have to tell it facts about Belgium, all right? Dinosaurs, Oxford English Dictionary, huge amounts of facts. And actually, there was a contest with these two Jeopardy champions in 2011, and Watson won. But you could see, they showed the audience Watson's top 5 guesses with the various probabilities. And you could see the guess that it gave was often right, but there were some others in those 5 that showed the computer had absolutely no understanding. It was completely off beam on a totally different track. So the question that really was raised by Luciano, which I agree with, is this is artificial intelligence, but it's simulated intelligence. My hero, Richard Feynman, and I tend to mention him at least once in a talk, gave a popular talk on computers. And what he said was, it's like a dumb file clerk. The inside of a computer goes like mad, is as dumb as hell, but it goes like mad. So you can imagine the file clerk going back and forth, but all he's doing is reading what's on the card and doing what's on the card. And that's what computers are. But the real challenge then is our neurons are very simple, slow things, and we have, nearly 100 billion of them. Why is it that we have self-awareness, intelligence, consciousness? Is it conceivable we could produce such a thing? Will we have sort of R2-D2 coming on stage, assisting us in our fight against whoever? Or will we have a sort of dystopian world with Skynet, evil computers taking over, trying to wipe out humanity? Or will you end up falling in love with your operating system, right? Which is one of the possibilities done here. So I think that these are highly unlikely, certainly not before the next Thinking Digital conference next year. So I think we're safe. But it is interesting that people like Bill Gates and others have raised problems. I think it's a little premature, but I don't think the singularity is around the corner. In fact, I'm very skeptical of the singularity, but I'll leave Stephen Hawking with the last word. Success in creating AI would be the biggest event in human history. Unfortunately, it might also be the last. Thank you. Thank you.
I guess just really at the end, you kind of gave fairly. I guess like Luciano says, you come across. You obviously identified yourself as as an AI skeptic, or certainly singularity skeptic.
Singularity skeptic, yes.
Yeah.
I break my cover. Right.
So just to make the distinction, so AI, is that something you feel is going to happen?
Oh, I think these weak AI applications are going to be everywhere, and I share the concerns that they will take out jobs, and it's not obvious there will be jobs to replace them. So I think there are real things, and I'm worried about the links. I was in UC Davis last week talking to a guy who works on security, and his student came up and said, look, he said, I've been... The electrical grid connects the dams in California. There's a dam called Hetch Hetchy Dam. He said, look, I can open the sluice gate on Hetch Hetchy Reservoir. That is really scary. And so that's what they're trying to do, to make these things much less vulnerable. So I think there are vulnerabilities, and that's what worries me. And, how many, your car has 30 processors or more, how many millions of lines of code, how many errors? These are scary things. So that's our challenge.
Okay,
for the next conceivable
Yeah.
10, 20 years.
So, I mean, all the stuff that Kurzweil talks about in terms of this like merger between sort of body and machine and computing, is that something for you that is basically sci-fi? Would you?
Yes, I think it's sci-fi. His argument is about Moore's law exponential continuing, but actually, I'm a physicist. You're getting down to almost atomic dimensions, and the technologies will change, and it's very unlikely that Moore's law will continue in its present form. It's going to continue increasing for a while, but it's not going to continue in the linear form that he assumes.
Okay.
So,
as a technology observer, if you will, as opposed to expert, I guess there's some sense, is quantum computing going to represent any hope to sort of next generation of beyond silicon?
Well, quantum computing, I'm very interested in quantum computing, but I actually don't believe, I edited these lecture notes by Feynman on computing. He lectured for the last 5 years of his life on computing, and he sort of came up with a quantum computer and realized it was not the same as a Turing machine. So it can do things like factorizing large numbers on which our security systems are based. But in order to factorize something useful, you have to have millions of gates and millions of qubits, and that's a long, long way off. So I don't think that they will be practically useful in that sense, and they certainly won't replace your iPad. Right?
Okay. So we will
but
see.
I think it's interesting.
We'll see the end of the road of Moore's law before we see quantum computing come in.
Yeah, quantum computing is not going to be a general purpose thing. There's only about 2 or 3 algorithms that can do anything useful. So I don't think it's a very special purpose thing. I think there will be quantum devices doing interesting things, absolutely. But I don't think they'll be replacing computers anytime soon.
Right. Okay.
Sorry about that.
No, that's all right. Very interesting. Thank you very much, Tony.
Thanks very much.
Cheers.